All right, so let's get started. Today we will talk about the physical layer, which is I really love the physical layer. It's a fascinating thing. So we will talk about the minimum distance receiver, pulse amplitude modulation, and something called Nyquist pulses. Short review of what we have done. We have talked about the OSI model. And we have talked about the internet model and how they are not really well translating to each other, but roughly, only roughly. So there's 7 layers in the OSI model. Well, actually it's only 5, but the topmost layer is called 7. Internet model, we will use 5 layers, looks something like this. We talked about the protocol suites for TCP/IP. And we talked about addressing, internet names, IP addresses, link addresses, DNS and ARP. And we did a long example on how to move an IP packet over several routers from the beginning to the end, right? And we talked about the OSI reference model in more detail. It looks something like this, where we have end-to-end protocols and we have protocols that work over several hops to get from one end to the other end. And what else? Yeah, so that's what we've done. So right now in the course, what we have done, remember we have started talking about the applications and then worked our way down in the stack and given this example about IP, how to move IP packets over a network, or an internetwork actually. So now what we will do is we will talk about the physical layer for some time, and then as the course progresses, we will move up to the data link layer and maybe touch on the network layer again a little bit. So now we would start to do things a little bit more seriously here and then talk about this in detail. All right. So there is models for everything, right? So the people that work in the physical layer loves this model. It's called Shannon's communications model. And Claude Shannon is the founding father of a branch of, I would say applied mathematics called information theory. So he's really a big shot. He did some very, very nice work from during the 1900s. He died just a couple of years ago, 10 years ago, so maybe not a couple of years ago. But he was an amazing researcher. And what he did, he formulated this model, or this model has been named after him. He didn't formulate the model per se, but he worked on all of these things in his career. And how he thought about communication is that we have a source here which generates some bits. Okay? And the objective of a communication system is tied to replicate these bits at this end. So we would like to make the bits here be replicated here. So we select the message here, 100111, and we would like to get the same bits here. That's it, right? So how can we do that? Well, what Shannon said, okay, the first thing we should do is to look at this stream of bits and see whether there are unnecessary bits in this. So we want to do some type of data compression here. And we know that you probably use data compression on a daily basis when you're looking at pictures on the internet, for instance. These pictures have been taken with a high resolution CCD, and then it's been producing a bunch of bits, and these have been compressed down to a JPEG. And the same thing goes with video. It's not raw video that you look at, it's a compressed version of what the video camera saw. So data compression we do here in order to reduce the number of bits to, say, just 3. So let's say that we started with 5 bits and then we have only 3 bits left. Of course, we work on much longer blocks than this, but just to get an idea. So this is data compression. So what we have here are the important bits. Okay, these bits can then be used in order to decompress into the red bits. So there are compression methods here which are lossless, in the sense that if I had the blue bits, I can get back to the red bits. And you also use them sometimes when you have a text file which you compress with your zip command or something like that. You can unzip it and you get back exactly the same document, right? The thing I talked about, JPEG and video encoding, are lossy encoding where you cannot recover the original source. But the thing is that the picture and the video you get is good enough for human consumption, so you don't care. You don't care about the original as long as it looks good after compression. Okay, so after here we have really the crucial bits, the 101s here. And then we would transmit this over a channel which would introduce noise. And from here to here, there will be errors. So it is not clear that these bits might be flipped or changed when transmitted over the channel. So what we do then is that we add some control bits to this in the channel encoder here. So then we're back to maybe, 4 bits here. I don't know. So a little bit extra bits. So we add here a protection bit. The last bit here is a protection bit. And then it goes from bits to a signal in the modulator here. Oh, sorry. So the process to go from here to here is called channel encoding or error control coding. So we add control bits to this in order to fix errors at the receiving end. And then we have bits here, which are just binary numbers. And we would like to convert that into some type of waveform which fits the channel that we have. Could be a radio signal or electrical signal or an optical signal or something like that, depending on the medium. But there will be some type of signal here at least. And then the nature is so bad to us, it gives us noise like this. There is nothing we can do about that. So at the receiving end here, we would have a signal which is basically looking like what we transmitted, but with some noise on top of it, like this. It could be more or less depending on the signal-to-noise ratio. And the objective of the demodulator is to observe this signal, the received signal, and trying to figure out what bits were transmitted. Okay? If the demodulator could see the purple curve here, it would be no trouble. It could invert this method without errors. What is going to cause errors is the noise which is added on to the signal here. So it could be that the output here would be 1, 1, 1, 1, for instance. That there is an error here. You see that here this second bit was flipped. Okay, so the output might be there. But the purpose of the check bits here is that the channel decoder can look at this 1, 1, 1, 1. It looks suspicious. I think there is an error in the second position here. And therefore, I will simply output 1, 0, 1 here. If everything is working, right? Of course, there could still be remaining errors after trying to check and detect errors, detect and fix errors. But if everything works as supposed to, we can tolerate a number of bit errors here and still be able to recover the input bits to the channel encoder, the blue bits here, which are the bits we care about. We don't care about the green bits, we care about the blue bits. And then with the blue bits, we can then recover the message by using source decoder, and then everybody's happy. Okay, so that's the channel communication model. How does this fit into the OSI model? Well, essentially, this part is the physical layer. It transmits bits over a link. That's the objective of the physical layer. While this source encoding and decoding is typically placed in the presentation layer. Okay, so this is, and let's put it in the application layer. So we won't talk more about this, but we will talk about this in some detail. Today we will talk about these two green blocks. Okay, so I think that's setting the scene. So let's get started. Or are there any questions here? Oh, okay. So this is what we want to do, both today in the lecture and what you want to do in the project. The objective is to transmit bits. So we have some bits, B1, B2 up to B capital K, a block of bits here that goes into the modulator block and then produces a signal. The signal is then transmitted over a channel which adds noise. Okay. So noise. Here we have the transmitted signal, and here we have the, sorry. Tx for transmit signal and Rx for receive signal, like this. Okay. The demodulator observes the received signal, which is a distorted version of the transmitted signal, and try to invert the function of the modulator in a smart way, the demodulator here. And it outputs then a string of bits. These bits are the demodulator's best guess on what these bits are. So these are the transmitted bits, and this is the best guess of the receiver what the bits were, right? So this is guess or decision, same thing, on B1. Sorry, on B1. Like so, B1 hat for guess or estimate, right? It's nothing to do with Fourier transform or anything like this. It's just a notation. So B hat means our guess on B. Ideally, B hat should be equal to B. Then there is no error. But it could be that B hat is not equal to B, then we have an error. So the beauty about the digital communication is that either we have a correct thing or we have the wrong thing. There's nothing in between. Okay. So this modulator, what it basically is a simple mapping from bits to a signal. So if we have the pattern 0, 0, 0, then the output would be S1. If the pattern is 0, 0, 0 and then a 1, then the output would be S2 and so forth. Right? So it's basically just a translation device where you can think of the input bits as index the output signal. Right? Very simple device. So that's not the problem. The problem is in the receiver, as we will see later on. So the modulator is quite simple. Just input bits, output the corresponding signal. That's all it does, nothing else. So the modulator maps all possible k-bit patterns into a signal alternative, and we have a number of signal alternatives. How many do we need? Well, if we have a k-bit pattern, we know that we have 2 to the power of k possible inputs, which means that we need 2 to the power of k possible outputs. Right? The received signal is then the transmitted signal plus noise. The problem is that the receiver doesn't know whether S of t, the received signal, S of t here, is it S1 or S2, S3, S4, up to Sm. That's the problem, right? It needs to figure out what is the most likely S when we have observed R. Okay, so R is the input data to the demodulator, and it needs to figure out S. And it has no clue of what the noise is. I mean, if the demodulator knew the noise, you could just subtract it and then we're done, right? So that's no fun, right? There's no problem left. So fortunately, that is not the case. Okay, so the demodulator, what it does, it maps each possible signal, all possible R's needs to be associated with a decision or a guess on the transmitted bits. Okay, so R, it's a mapping from R to a sequence of bits. So that there is some rule in how this is done. Any questions so far? So to make this concrete, suppose we have our bits here, 0, 0, which is then mapped onto a signal alternative, and perhaps it's something that looks like this. So this is our first signal alternative, some square wave. Let's put in some variables here. And then we have 0 to 1. That's mapped to another signal alternative that looks something like this, perhaps, where this is t. So this is S2 of t. And then we have 1, 0. It's mapped to I don't know, maybe this. And then we have 1, 1 being mapped to maybe something that looks like this. This is S3, this is S4. So you get the basic idea, right? So the modulator is determined by a set of signal alternatives and then a mapping from the bits to the signal alternatives. And we might have this mapping that 0, 0 maps to S1, 0, 1 to S2, 1, 0 to S3, and 1, 1 to S4. It's just a convention. We can flip this around as we like. Okay. So that's pretty clear how the modulator works. Let's work on the demodulator. Before that, so a simple quiz here. Now, suppose we want to transmit 4 bits. How many signal alternatives do we need? 4, 8, or 16? Give you a few seconds to think about this. So how many for A, B, or C? Excellent. Excellent. So 4 bits is 2 to the 4 possible alternatives, and 2 to the power of 4 is 16. So what does a demodulator need in order to decode the transmitted bits? The bit to signal mapping, the signal alternatives, and the observation of the received signal. So then there is some excess in different alternatives here. So how many for A, B, C, D? This was more difficult, right? Okay. So first of all, for sure we need the observation, right? We need to look at the received signal. It's hard to do anything without an observation. So let's assume this one is not, this one false, okay? Now the question is, do we need the signal alternatives? Do we need knowledge about the shapes here? Yes. Okay, so we need the signal alternatives. So this one goes out the window also. And the question is, do we need the mapping from bits to signal alternatives? And yes, we do. Right? We need how to associate a signal alternative with the corresponding bit pattern. So, which leaves C. Maybe this was a bad question on a Friday afternoon. I don't know. Yeah. Okay. So let's continue. So this is what we want to do. And I will try to motivate why this is the way, what we want to do, right? We want, our task, we're the receiver now. Our task is, given the bit to symbol mapping, the set of signal alternatives, that is, we know the shapes of the signals. Of course, we don't know which signal has been transmitted because that's the task, right? But we know what the alternatives are. And we have an observation of R. Okay, so what we want to do now is to do the following. We want to compute the distance between the received signal and all signal alternatives. Okay, distance. So what is meant by that? It is so we can define distance between two signals, R and SL. We can do that by taking the difference between them and then put these double bars around that, and that is what we call the distance. And what these double bars basically means is the square root of the integral of the absolute value of that function squared dt. Okay. So why is this a reasonable distance? So if I'm interested in the distance between two signals, let's call them x1 and x2. What would I like this to be? It should be greater than 0. Okay, distances are greater than 0, so we don't talk about negative distances. We want this to be equal to 0 when x1 is equal to x2. Right? And we want it to be symmetric. We want the distance from x1 to x2, what the distance between x2 to x1. Symmetric. And if you check this equation, it fulfills all these things, right? First of all, the absolute value means that it doesn't matter if I take r minus s or s minus r, I will get the same thing. The square means that it's always positive. The subtraction here means that if r is equal to SL, I integrate 0, I get 0. Okay, so it's sort of like a meaningful distance metric. But it's actually much deeper than this. There is a whole theory about looking at signals as vectors in a vector space, where this thing here is the norm of that vector. Okay. So if you have seen that type of mathematics before, that's what's going on here. We won't go into that in much detail here. We just take this now as a definition of something that we call distance. Now, if I computed the distance between what we have seen and what all the possible things that we could transmit, right? We can put in L equals 1, 2, 3, 4 up to M. Then we get a number of distances. Which is the most likely transmitted signal then? Well, let's pick the signal who's closest to the received signal. Right? That seems to be, it's most similar to what we've seen, right? We saw a distorted version of what was transmitted. We compute the distances to all possible things that were transmitted. And then we pick our choice. We choose the one which is closest to what we've seen. Right? If there was no noise, then ROT would equal to one of these. And then the distance for that would be 0. And the distance to all other ones would be greater than 1, right? Since we have different signals here. Okay. So this is a quite reasonable rule, I would say. Just pick the signal alternatives which is closest to what you see. Okay, so let's do that. So we pick the index m hat as the arg min over L of dl. So this is just notation. So what does this mean? Well, first of all, arg min of dl before I'm saying, okay. So here's what it is. dl is a function of L, right? For different signals here, we get different numbers, and we get positive numbers. So here's the distance to signal alternative 1, 2, 3, and 4. So which one should we pick in this case? Well, we should pick the one which has the closest distance, which has the smallest distance to what we have observed. So we would like to pick this one. So we're not interested in the minimum distance. That's the minimum here. We're interested in the index L that produces the minimum distance. Okay. So we're not interested in the minimum. We're interested in the index that produces the minimum. So that's why arg picks this thing that minimizes this. Okay. So is the notation Clear now? So arg min of something is not the minimum, it is the value of L that corresponds to the minimum distance. Okay. And we can look at the distance or we can look at the distance square, it doesn't matter. Why do we want to look at the distance square? Well, then we don't have to take a square root here. Right. Sometimes less things to write down. That's the only reason for this. Okay. So, continuing our example here. So suppose we then receive the signal that looks something like this. Okay. Then we can already now expect, okay, maybe it's this signal, right? Then it's not so hard to do this visually. But if we have a very noisy signal, like this, it's difficult. Okay. So we cannot just take a sample of this and figure out what is right. When we have something noisy, we need to do something smarter. And the smarter thing is to compute these distances and pick the minimum distance. Okay. So then, yeah, so basically we form the distances as we did here, right? We just take whatever we receive, we subtract off one of these in turn, form the absolute value, integrate, and then we get a number. And then we just plot these numbers like this. And then we pick, okay, it's hard to see, but this is then m hat guess that. So this is equal, in this case, equal to 4. So if we pick m hat equal to 4, that is the same thing to say that we guess that S4 was transmitted. Right? And if S4 was transmitted, our guess on the bits is 1, 1. Okay. Like this. Okay. So, are there any questions on the receiver now? This minimum distance receiver. Its functionality. Okay. So actually it's a fairly simple device. We just take the received signal, we subtract off all the possibilities and figure out what the distance is to all the possibilities, and then we guess that the ones which has is closest to what we've seen is our guess. Minimum distance receiver. Okay, so is that it for the physical layer? Well, in principle, yes. So this is what we want to do, but we still haven't said anything about how should we select these signals? What is a good choice to the number of bits here? And what is the performance differences for the minimum distance receiver when we make these type of designs? So let's go into that. Okay. The workhorse of physical layer is something called a pulse amplitude modulator. I would say that most physical layers can be put into this form. Not everyone, but most of them. And we will only work with these type of physical layers in this course. So pulse amplitude modulation is very commonly used. The input are bits. Okay. And then there is something called a mapper. And the mapper just takes a block of input bits and outputs an amplitude. Okay. So previously, when we talked about the modulator, you output a signal, but here we output just an amplitude and then convert the amplitude to a signal. Okay. So bits coming in, they get blocked into k consecutive bits, and then mapped to an amplitude, which we call capital A here. The possible amplitude we call capital A1 up to capital AM, where M is 2 to the power k. Similar to what we did before. And the output then is, we call that AK. So that's an amplitude, and it's in this set curly A, and curly A is A1, A2 up to AM. So these are the possible amplitudes, and we call that the symbol alphabet. Okay. So bits in, symbol amplitudes, symbols or amplitudes out. The amplitudes can be one of the numbers in the symbol alphabet. Okay. Now, the next step is to take that amplitude and multiply that with a pulse, G, to form the output signal. So we see in an example here that the output signal, S of t, is a sum of pulses. And the pulses is that we take the kth symbol and we multiply that with the pulse G, and we delay it with k times capital T seconds. So this is a pulse train, where the kth pulse has an amplitude which is equal to the kth amplitude, and the kth amplitude depends on a block of bits. Okay, so we have bits, symbols, signal. Okay, once more. Bits, symbols, pulses. We add the pulses together, we get the signal. So let's make an example. First of all, our symbol alphabet. Let's make that -3, -1, 1, and 3. Okay. This is a typical alphabet. It's symmetrical around 0 with equal distance between the amplitudes. So you see here, there is a distance 2 between all amplitudes here, right? Then we need to define a mapping from bits to symbols, okay? And these are working with the BI here is the ith bit, where I is the time index, and K here is also a time index. But since there are several bits corresponding to a symbol here, the time scales are different. Okay, so there are K bits before we have one amplitude. So if we do this mapping, things are okay. So the kth symbol needs 2 bits, right? And to find the 2 bits in the sequence of bits, we take an even bit and an odd bit. 2 consecutive even and odd bits produces one output symbol. Okay. And the mapping is simply like this. For instance, that 0, 0 gives us -3, say, 0, 1, -1, 1, 0, 1, and 1, 1, 3. Okay. This is not a particularly good mapping. We could do better, and that will be obvious a little bit later. But let's just do this for an example. And then we need to specify a pulse shape, G. This pulse shape, G. And let's just take a square wave. And then we need a time, T, which is the time between consecutive symbols. And the duration of G and T are in principle unrelated. So we can just pick T to be this value. It doesn't necessarily have to be the duration. Often the case, but not necessarily true. Okay, so then, if we then have into the mapper, suppose we have here now I equals 0, 1, 2, 3, 4, and 5, like this. And then we have the corresponding BI here. So say 0, 1, 1, 0, 1, 1 could be one example of bits, right? Then if this is the input to the mapper, the output of the mapper would be defined in K and AK. And since there are 3 blocks or 2 bits coming in, there are 3 symbols coming out. Okay, so it's from K equals 0, 1, and 2. Right? So we have 2 bits in, 1 symbol out. 6 bits in, 3 symbols out. So what is the first symbol?
-3?
Aye. -1. Why is that? 0, 1, 0, 1, -1, right? Second? 1, I think, yes. And then the third is just 3, like this. Okay. So that's the mapping, right? And now let's convert this into the signal. So it's a sum from -infinity to infinity, a k g t minus k t. Okay. So here, every t seconds, we start a new pulse. We transmit a new pulse. Okay. So for k equals 0, put in k equals 0 here, we see we have a0 times g of t. Okay, so -0. So we get a0, which is -1, multiplied with g of t. It will look something like this. So this is a0 times g of t. That's our first pulse, which corresponds to the first symbol, -1. Right, so let's put this amplitude to C, say. So this is then -C. Okay. Second pulse, amplitude 1. So 1 times g of t, but then shifted t seconds. So it will start at this point, like this, where this is C. So here we have A1 g of t minus t, like this. Okay, and then we just continue. So the third symbol happens to be 3. So then we will have something like this, and this is then a 3 times g of t minus, a2 g of t minus 2t, like this. And then we just continue. So if we sum all these pulses together, we get this sum, and there we get the transmit the signal. So any questions on this? So what I want to stress now is that pulse amplitude modulation is defined by a bit to symbol mapping, a pulse shape, and the time between consecutive pulses. That's what we need in order to specify this. So if I change t here, I change the spacing between the pulses, and they could potentially overlap also. That's not forbidden. If I change the pulse here, I would change the shape of each possible pulse. If I change the mapping here, I would change, basically for a given bit sequence here, I would change, the amplitudes. I would be permuted in some way. Okay. Any questions? No. Okay. Now, the second thing, so now we know pulse amplitude modulation, how it works. But something which is super important that we care about is data rate. So what is the data rate for this type of system? The easiest way to figure that one out is to go backwards. Okay? So how many symbols per second do we transmit? Well, how many symbols per second do we transmit? Well, we transmit one pulse, that is one symbol, every t seconds. So the symbol rate is 1 over t. Right? Okay, so now we know that. We transmit one symbol every 1 over t seconds. So the symbol rate is 1 over t. How many bits do we transmit per second? I mean, it's there on the slide, right? So it's a little bit cheating, but think about it, right? Every symbol carries a number of bits, at least 1 bit, but it can carry 2 bits, 3 bits, 4 bits, 6 bits. We don't know, right? Oh, we do know actually, but we can design this. So depending on the number of bits that each symbol carries is the log 2 of m, well, which is also k. We have k bits, and k is, m is 2 to the power of k. M is 2 to the power of k, so if I'm interested in k and have m, I take the log 2 of both left-hand and right-hand side. Okay, so log 2 of m is also k, the number of bits. Okay, so for each symbol I transmit k bits, and therefore the bit rate is the symbol rate times the number of bits per symbol. So log 2 of m divided by t. So now we know how to get high data rate. We care about this. So how do we get, give me 2 ways to get higher data rate. Suggestion for something. What could be changed in the design to get high bit rate?
Faster sampling and also more bits per symbol.
Oh yeah, both of them. So we can reduce t, so transmit pulses quicker, and we can increase m to transmit more bits per pulse. So these are the 2 things. So what is stopping us from doing this to have high data rate? That's a rhetorical question now, but you might know it already. There are 2 things that stop us from doing that, and that is the noise level on the channel, because it turns out the more bits we transmit per symbol, the more sensitive we will be to noise on the channel, and we will get more errors. The second thing, which is not so obvious, is that the quicker we transmit pulses here, the higher the bandwidth of the transmitted signal is, and it will then occupy a larger bandwidth, and bandwidth is a natural resource which is scarce. Basically in radio it's very important to keep the bandwidth of the transmitted signal as small as possible. Right? So we can get high bit rate only if we have a channel where we have relatively little noise on, or when we have a channel with a lot of bandwidth. Another way to turn it around is to say that if we can increase the power of the transmitted signal, we can defeat any noise we like. So we can we increase the data rate by increasing the power of the transmitted signal and or the bandwidth of the transmitted signal. And the trade-offs of this is what we will explore now, next lecture and next hour, and then the following lecture. Okay, so let's take 15 minutes.